Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark, and the host and speaker of today's exciting event. I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign and the technical director of the Fabricated Geomembrane Institute. This is our 11th webinar of 2020, and the remaining 4 webinars for 2020 have already been scheduled with some great speakers and timely topics, which are available on the FGI website. And the next webinar on October 8th is on the last slide today. So I hope you'll see who our next speaker is in the webinar series. During today's webinar, I welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and I will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides that I'll use today will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar, so you don't need to send a message. It will come to you automatically. Okay, so today the title of the webinar is Geomembrane Wrinkles in Containment Applications, which is an important and timely topic for the industry. So let me get going here. And yep, here's the outline. First, I want to talk about subtitle D requirements, a composite liner system, and then get into wrinkles and how we can calculate wrinkles. So this is a portion of the subtitle D regulation or guideline from the US EPA. And I want to focus in on the red text. In the absence of an underlying low permeability soil liner, flow through a defect in a geomembrane is essentially unrestrained. The presence of a low permeability soil liner beneath a defect in the geomembrane reduces leakage by limiting the flow rate through the defect. And that is essentially the importance of having intimate contact between the geomembrane and the underlying low permeability soil. So that was recognized as part of subtitle D. So let's go a little further into subtitle D. Under the geomembrane sections, it says the recommended minimum thickness for all geomembranes is 30 mil, with the exception of high density polyethylene, which must be at least 60 mil to allow proper seaming and stress crack prevention. So any geomembrane that's 30 mil is acceptable under subtitle D. And I'm going to get to this at the end of the presentation, where all we have to do is show that the geomembrane is chemically resistant to the application, and as long as it's 30 mil thick, it can be used. More importantly, in subtitle D is this last sentence in this section. Some geomembranes can be manufactured by a calendering process with fabric reinforcement called scrim to provide additional tensile strength and dimensional stability. That is the key, dimensional stability. So that's what's causing the wrinkles, is a lack of dimensional stability. Dimensional stability is basically you take a 1 foot square piece of your geomembrane, you put it in the oven, and you measure how much it shrinks or changes shape in the oven during thermal exposure. So even in 1988, the US EPA recognized the importance of dimensional stability of the geomembrane and included it in subtitle D, the section on geomembranes. This regulation or guideline, subtitle D, became effective in 1991. So it's been in effect for almost 30 years. And dimensional stability was understood way back in the 1980s. So that's really the crux of the wrinkle issue, is getting materials and geomembranes that are dimensionally stable. Okay, so let's quickly talk about the composite liner system. This is an MSW facility with I'll call it an enhanced composite liner system. It's pretty close to a double liner system. Here's a low permeability compacted soil subgrade / liner where my laser pointer is. There's the secondary geomembrane sitting over top of that low permeability soil. A geosynthetic drainage composite as a witness zone, a geosynthetic clay liner above the witness zone, but below the primary geomembrane where the laser pointer is. So let's go to the secondary geomembrane. If there's a defect in that geomembrane, a hole in it, the low permeability soil directly beneath it, and you can see the geomembranes laying fairly flat and in intimate contact here, the leakage through that defect would only be due to the area of the defect. And that would be the same with the primary geomembrane at the top in intimate contact with the geosynthetic clay liner. So it's really important that the geomembranes, whether it's the primary, secondary, are in intimate contact with the soil barrier below it, whether it's a GCL or a compacted soil, to limit the area of leakage to the size of the defect. And you'll see that in the calculations in just a minute. Okay, so here are the calculations. We use Darcy's law. The flow through the compacted soil is Q, or the leakage, and that's the hydraulic conductivity of the compacted soil times the gradient acting over it, and that's basically the height of the leachate above the compacted soil liner divided by the thickness of the soil liner. And then the most important term is A, the area of seepage. So without a geomembrane, the area of seepage is the entire area over which leachate is ponding. So if I have a 10-acre cell, I have to multiply Ki by 10 acres, and you can see that would yield a very large amount of leakage. So that was the idea of coming up with the composite liner system in subtitle D, where the geomembrane is across the compacted soil. And so if there was no defect, and I'll put my laser pointer over the defect in the geomembrane, in theory, there would be no leakage because the leachate is separated from the compacted soil, and the transmissivity or permittivity of the geomembrane is like 10 to the minus 12. So it's very low. So you could say that that would be basically no leakage. But now let's put a defect in the geomembrane right there. So if there is intimate contact between the geomembrane and the compacted soil, the area of leakage is only the defect. And so that was what is highlighted in subtitle D, that the area of leakage is only the defect, and the importance of intimate contact. Okay, so J.P. Giroux 2017 says even with third-party CQA of the geomembrane installation, you can expect 5 to 6 defects per hectare. If there's random CQA, sort of spot inspections and so on, you can expect 20 to 25 holes per hectare. And then, of course, if we can get leak location performed, we could migrate that down to 0 defects. And I'm going to talk a lot about leak location and the importance of minimizing wrinkles in just a minute. Okay, so this is the situation we want. We want intimate contact and only the area of the defect controlling the amount of leakage. And we can estimate that Q through the defect using Giroux's 2017 equation that's shown here, and I'll illustrate this on the next slide with some calculations. The key parameter is this area of hole. Okay. All right. So here's some sample calculations. I vary the area of the hole from 1 to 4. So that's 4 times the size range of the hole. The diameter ranges from 1 millimeter to 3 millimeter. And just for the calculation, I use 4 holes per hectare. So the important calculation is all the way on the right, where the leakage, if there's intimate contact, ranges from about 1.3 to 1.6. So if I use a round number, I say there are 4 holes per hectare. There's about 1.5 liters per hectare per day. Okay, I want you to remember this number 1.5. So if there's intimate contact, we have about 1.5 liters per hectare per day of leakage with intimate contact. You'll see in just a minute, I'm going to compare this 1.5 to if we have wrinkles and we lose the intimate contact. Okay, so let's talk about field intimate contact. Do we actually get it? So here are a couple projects that actually look pretty good in terms of wrinkles and intimate contact. Most importantly, you can see on, let's start on the right here, there's some small wrinkles here. This one is pretty connected. It's running along the sheet, but not across the sheet, which is good. So there may be some leakage parallel along that wrinkle, but not across it. And maybe the same on the other side. So you're looking for not only the height of wrinkles, the interconnectedness of the wrinkles. Now, let's look at this particular project. So you can see wrinkles in both directions. So now in this particular application, you have a much larger area of seepage in which you're going to use to calculate the leakage rate. Okay, and area of seepage gets multiplied directly by Ki, so it has a big effect. Here's another such installation. You can see wrinkles throughout. They're all interconnected, so this is, again, a large area of seepage. The wrinkles remain, and especially there's some discussion that with textured sheet, it does not remain. They do remain even with textured sheet. Another area where a lot of wrinkles shows up is at the toe of slope. So if you look across this facility, look at the toe over here, you can see some wrinkles developing and moving towards the toe of that slope right here. Okay, another place wrinkles develop are during construction and pushing cover soil out. You can see this dozer has pushed some material forward and the geosynthetics are wrinkling up front. And this is an issue because then the wrinkles sort of get pushed in one direction and they accumulate, and then they have to be dealt with. Usually that involves cutting out the wrinkle, which I'll talk about in just a minute, with different forms of patching of that cutout. Then finally on the right is 2 geomembranes being installed at different times. So the one on the right with the wrinkles was installed the day before. The one on the left is the current day, so it's still fairly unwrinkled. But now you have a problem trying to weld those 2 sheets together. So it's best to weld rolls if you're going to use a field fabrication situation versus a factory fabrication to weld the geomembranes that are rolled out on the same day. So you can get a good weld between the 2 rolls. Okay, so let's talk about wrinkle behavior. Do they stay? Do they go? So Song and Kerner in 1998 ran some box tests in which they created a wrinkle and then applied a stress to the top to see if the wrinkles would go away after application of the stresses, the applied stress. The wrinkles flattened a little bit, as you can see on the right here. So the original shape of the wrinkle is the top line. After 100 kPa normal stress, it decreased from the original line to here. And then at 1100 kPa, which is, let's see, 2000, that's like 20,000 pounds per square foot. So really high load. The wrinkle's a little smaller, but still there. So the wrinkles do not disappear. So do we see that in the field? So here are two photos from Kerner and Kerner 2013 of some exhumed geomembranes, and the wrinkles are clear on the right, exhumed wrinkles, and here's a wrinkle being entombed, creating a dam which impedes the flow of the leachate on the left. Here's another example. This is the Kettleman Hills hazardous waste facility in California. Underwent a slope stability problem, which is on the lower right, but that allowed excavation of the waste and examination of the liner system. This is the top of the compacted soil liner on the right, and you can see striations indicating shear movement. And then on the left is the geomembrane that was over top of that compacted soil. And you can see the matching striations in the smooth geomembrane on the left. But if you look closely, you can also see the wrinkles that were present when the geomembrane was installed on top of the compacted soil liner. So even after 100 feet of hazardous waste, usually weighing about 110 pounds per cubic foot, the wrinkles are still present. And across this piece of geomembrane, you can actually see the geomembranes connected. The wrinkles connected as well. In 2017, Professor Kerry Rowe gave some summary dimensions of wrinkles. Typical wrinkle width is about 0.7 to 1 foot. The typical wrinkle height of about 0.2 to 0.7 feet. And the area of wrinkles varies from about 2% to 30%. So even at 30% of the area of the cell or pond, that's going to be a large area that you'll have to include in the leakage calculation. Typical wrinkle length, if 5% of the area has wrinkles, is about 655 feet. So these wrinkles are interconnected and allow flow through the wrinkles, and thus a much larger area of leakage. This is a photo from Professor Rowe's field site in which he has various geomembranes installed, and you can see the wrinkling in many different directions. The next slide puts some yellow lines on top of this from one of Professor Rowe's presentations, and you can see there the interconnectedness of the wrinkles, and thus a much larger area of seepage. So finally, Professor Rowe concludes in 2017, if there are 5 holes per hectare, remember that was good CQA at the beginning, 20% of the entire area is occupied by wrinkles. There is a 67% probability that 5% of the entire area is occupied by wrinkles, and there is a 23% probability that at least one hole, one of the 5 holes per hectare, is coincident with a wrinkle. And you'll see in just a minute through the calculation, these wrinkles will dominate the leakage calculation. So what do the states require? The states in the United States, there are 36 states that require intimate/direct contact between the geomembrane and the compacted soil or the soil barrier part of the composite liner system. There are 4 states that say minimize the wrinkles, and there are 7 states that are vague. So if I lump those first 2 together, I'd say 40 of the 50 states, 47 surveyed, require intimate contact, and we're not getting there. Okay, so what effect does this have on the leakage rate? So this is a slide from Professor Rowe and his calculation of the leakage rate, and that's this big Q down here at the bottom. The most important parameters in the calculation are the ones in red. L is the length of wrinkle. So you saw on the slide just a minute ago, Professor Rowe indicated a typical wrinkle length of 655 feet. So multiplying anything by 655 in English units is going to give you a lot of leakage. B is the width of the wrinkle, and theta is the other main parameter right here, and that's the transmissivity, or basically the ability of the liquid to flow between the geomembrane and the compacted soil liner, or the GCL underneath the geomembrane. So that's illustrated in Professor Rowe's diagram right here. So you have flow underneath or between the geomembrane and the compacted soil liner, or the GCL. This is the theta, or the transmissivity parameter that is going into this equation. So how do we get these three values to plug into the equation to estimate our leakage? So J.P. Giroux in 1997, good contact is a geomembrane with as few wrinkles as possible on a smooth compacted soil. And Professor Rowe assigns 1 times 10 to the minus 6, 10 to the minus 8 meters squared per second for good contact, and about 10 times higher for poor contact. So there's an order of magnitude roughly if you have good contact and poor contact, and that's going to come into this spreadsheet or calculator that I'm going to show you in just a minute. Okay, so using Professor Rowe's equation and typical values for wrinkle length of in meters, so 60 to 1,000, a wrinkle width of 0.2 to 0.8, 1 hole per wrinkle. The leakage would be, if I go to the far right column, liters per hectare per day. It would go from 4 to about 150. Now remember, at the start of the webinar, I gave you the leakage with intimate contact and 4 holes per hectare. And I said it was about 1.5. So notice, with just 1 wrinkle and 1 hole, not 4 holes, 1 hole, the flow or the leakage is 100 times that of no wrinkle. And that's what I meant, that the wrinkle is going to dominate the leakage calculation. And here's just 1 wrinkle, and it's 100 times intimate contact. So it's a really significant increase. Okay, so that brings me to the geomembrane defect and wrinkle leakage calculator. These are some slides that are in the presentation, which will be on the website, as well as, if I can jump out of this, I want to show you the calculator itself. So this is an Excel spreadsheet. You can download it from the FGI website, and you'll see that's the first page you saw on the slides. So you enter in the blue cells of the calculator, you put in the dimensions for the pond. So for example, 400 feet by 600 feet, 25 feet deep. You put in the hydraulic conductivity of the compacted soil, and then the hydraulic conductivity of the geomembrane, 1 times 10 to the minus 12. You can use this to estimate how much money you'll lose or leak if you put in the cost of water. In this particular case, I put in $25,000 per acre foot. And so without a geomembrane, just a compacted soil, you'd lose about $65,000. A geomembrane without defects, of course, you would lose 0. But we do have defects. And so down here, you can enter the number of defects. So again, the blue cells are what you enter. The other cells get calculated. So here's the compacted soil liner. In this particular case, I made it 5 feet thick for a particular state. I gave it 1 times 10 to the minus 7 centimeters per second, the geomembrane. And now I can put in the holes per hectare. So if I have good CQA, I put in 4. Remember, if you have random CQA, you would have 20 to 25, so I can type in 20, and you can see now I have 44 holes. If I go back to 5, I only have 11 holes, okay? You can put in the area of the hole here, change the diameter, and then finally the hydraulic head that acts on that particular defect. So in subtitle D, you're supposed to limit the hydraulic head on the geomembrane to 1 foot or 0.3 meters. But if for some reason you had a pond that had a higher hydraulic head on the geomembrane, let's say 30 feet, I type, or 30 meters, for example, I just type it in and all the corresponding values change. Okay, now we get to the defects and the wrinkle dimensions. So here we have a database built into the calculator for different geomembrane types. And I'm going to show you some photos of these in just a minute. But so for HDPE, a typical width is 0.85, a length using Professor Rose 655, LLDPE, a little smaller and a little shorter. PVC, or a more flexible geomembrane, much smaller wrinkles, and generally not interconnected. Flexible polypropylene, pretty similar to PVC. And so then I can move over in the calculator using Professor Rowe's equation I showed you just a minute ago. I get the leakage rate for HDPE, LL, PVC, and flexible polypropylene with good intimate contact and wrinkles, or poor intimate contact and wrinkles. And those two categories determine the value of transmissivity between the geomembrane and the compacted soil. And you can see it has a very big effect. Let's just take HDPE. Of course, it has the highest leakage, even with good contact, 250 gallons per day. But then if I have poor intimate contact, so I have a higher transmissivity, you can see it's almost 2.5 to 3 times, about 2.5 times higher than with intimate contact. LLDP about 2.5 times also. And now look at the more flexible geomembranes, and I'll explain why they have much smaller wrinkles, because of their modulus is much smaller. You can see that there's not that big of a difference. PVC maybe 5 gallons per day to 12, and flexible polypropylene 6 gallons per day to 14. So much smaller, orders of magnitude smaller than the stiffer materials. Okay, so this is a quick view of the spreadsheet, and if you come over here, this plots, you can get plots out that plot the leakage per day based on the pond volume, the money lost per day due to the leakage, and so on. So this calculator is on the FGI website, and it's free. If you have any questions using it, please let me know. So let me go back to my PowerPoint. And that gives you a quick way to assess the amount of leakage per different geomembranes very quickly. Okay, and I went through that slide. Okay, so the effective wrinkles. The observed leakage with wrinkles is 100 to 1,000 times greater than that calculated even, and this is from some field data. These wrinkles cause localized stresses and strains, which can be locations of stress cracks based on the Song and Kerner study. They interfere with drainage above the geomembrane. In other words, they create little dams and block the flow of the leachate to the sump system. If GCLs are present, this can lead to bentonite migration due to slopes or just applied pressure. And these wrinkles, of course, can lead to increased construction damage because they get caught on equipment or pushed in front of the equipment. Finally, the wrinkles have been impacting leak location surveys. It's Really easy to conduct a leak location survey with a smooth geomembrane that's in intimate contact, as you see in this photograph on the right here. In this particular case, the squeegee is in intimate contact with the geomembrane. It's not running over wrinkles, makes it a really easy process. Okay, I talked about state regulations. All right, so leak location requirements, there are 8 states already requiring leak location. Ohio is in the process of requiring leak location. And to facilitate the leak location, Ohio is looking to limit the wrinkle size to approximately 4 inches. And I think this is an important step because if the states start requiring leak location, we're going to have to start controlling the wrinkle size. And I'll end with some recommendations, such as reinforced geomembranes to reduce the size of wrinkles. Okay, I mentioned that in the geomembrane leakage calculator that I demonstrated, we have a little database of wrinkle heights and sizes for the different types of geomembranes. How did we get those? By looking at geomembranes in the field. HDPE generally has the largest wrinkles, from 7 to 9 inches tall, 10 to 20 feet apart, generally interconnected. As you can see in this particular photograph, you can follow the wrinkles basically across the facility. These wrinkles impede flow and, of course, can lead to stress cracking. Lower stiffness geomembranes have much smaller wrinkles. These wrinkles may be closer together, but not interconnected. So here is an MSW, municipal solid waste landfill, with a PVC geomembrane bottom liner. You can see very small wrinkles maybe over right here, but otherwise very few wrinkles. And though the wrinkles over here, and I think they're actually seaming that particular panel there, they're not interconnected. So this is a really nice intimate contact geomembrane. In fact, the only problem with this photograph, and this would be a question for somebody at the end if they could figure this out, on slide 37, if somebody can figure out the real only problem with this photograph. And I'll give you a hint, it has nothing to do with the geomembrane. It's a stability issue. Okay, so let's talk about thermal expansion. So we've been running some tests on different types of geomembranes to measure the geomembrane coefficient of thermal expansion. So that's this alpha term right here, geomembrane coefficient of thermal expansion. If you look at this equation from Giroux and Wallace 2016, alpha is in the numerator. So the higher the thermal expansion, the higher HW, or the wrinkle height. The other key parameter for the geomembrane is E, which is the Young's modulus, or stiffness of the geomembrane. And that's why I mentioned stiffness or rigidity of the geomembrane just a minute ago. So the stiffer the geomembrane, or the higher E, the higher the wrinkle height. And that's why I called some of the geomembranes flexible, indicating sort of a lower modulus versus a stiffer or less flexible geomembrane. So alpha and E directly go into the height of the wrinkle. Of course, the temperature change, delta capital T, is important. The bigger change in temperature, of course, the higher the wrinkle. But the geomembrane parameters are the coefficient of thermal expansion and Young's modulus. So we've run some tests on different types of geomembranes. Here you can see HDPE smooth, LLDPE smooth, flexible polypropylene, and PVC. And on the right, using the equation I just showed you, all the way on the right is HW, or the wrinkle height. So you can see HDPE 92 millimeters, that's almost 4 inches. LLDPE is 58 millimeters, that's about 2 inches. FPP 27 millimeters is about 1 inch, and PVC is about a ½ inch. So the HDPE has about 8 times higher wrinkle than the PVC geomembrane, and that's based on the modulus and the coefficient of thermal expansion used in the equation that I just showed you for a change in temperature of 45 degrees Celsius. Okay, so that's all the good news. The bad news is if we have wrinkles and we decide to cut them out, we have to put a patch out in the production liner. So that's done a lot for HDPE for destructive samples and seam testing, as you see in these photographs here. This is the grinding to remove the antioxidants and waxes so the HDPE bead will stick, as you see over here. But that's going to require a big extrusion patch to cut out a wrinkle. And you'll see in just a minute, these patches are less stable than thermal hot air patches that I'll demonstrate in just a minute. So in addition, if you factory fabricate the geomembrane, you can install panels in which no destructive seam test is required on the production liner. And this can be done at the beginning of the day in the field. 80% of the welds are done in the factory anyways, where the conditions are clean, consistent, warm, and so you get consistent welds there. So by doing factory fabrication, not only do we minimize the amount of field destructive samples, we also get more consistent and better quality welds. So here's some data from Brian Queen of the Ohio EPA. He looked at or made a database of number of holes per acres for HDPE geomembranes. He says approximately 5 holes per acre. Approximately 5% of those holes are due to extrusion welds, and of course this is during installation, not afterwards during service when the extrusion weld is subjected to stresses and so on. So this is during construction. 85% of those holes are due to soil cover, and 8% is due to welding and waste placement. Okay, and there's an extrusion patch on the left. All right, so what did I mean by a hot air patch? So if I can get this video to work. So here's this is the same geomembrane, just white, so it would show up on the video. So you take the patch, there's the patch. Again, it's the same material, just white, so the video would look good. You heat it with a hot air thermal source that's in this person's left hand. You're basically melting the patch and the upper surface of the geomembrane. It's attached. And so this will yield a weld that's very similar to the thermal weld that's created for the seam, both in the factory and the field. So there's no extrusion bead or anything needed for this. When this person's done going around the edges with the hot air gun, right there, the patch is done. It can be tested using air lance or a vacuum box, just like an extrusion patch, as you saw on the prior slide. Touch up the edges, and that patch is ready. Okay. All right, so in summary, we wrap up with some recommendations, and then hopefully we have time for questions. In summary, wrinkles remain. With wrinkles, we do not have intimate contact. We are not complying with subtitle D, but most importantly, we're increasing the area of leakage, and generally that'll increase the leakage rate by a factor of about 100. Okay. The pond liquid, I'll talk about that on the next slide, because all we have to do is use that liquid to run a 90-90 chemical resistance test to allow us to use any type of geomembrane. If the geomembrane passes the 90-90 chemical resistance test, it can be used as long as it's 30 mil thick. It will comply with Subtitle D. The wrinkles will also impede the pond liquid moving to the sump, create little dams in the facility which prevent migration of the liquid to the sump area or removal area. I mentioned increased leakage, and the wrinkles have an impact on conducting leak location surveys. I mentioned Ohio looking to limit wrinkles to about 4 inches and allow easier application of leak location surveys. I think that's going to become the norm. So we should start looking for ways to reduce the wrinkle sizes. Okay, so recommendations: use flexible or reinforced geomembranes. Any of those geomembranes can be used as long as they're 30 mil thick and they meet 90-90 testing to show that they are chemically resistant to the leachate being used at the facility. So if it's an MSW facility or municipal solid waste landfill, you can do that by using a synthetic leachate and checking the chemical resistance of the flexible and reinforced geomembranes to that synthetic leachate. And that's available in commercial laboratories around the country and world. One other thing could be done is backfilling at night when the geomembrane tightens up. Of course, there are safety issues with working at night. It's been suggested light-colored geomembranes can be used, and generally light-colored geomembranes do reduce the size of the wrinkles, but there are still wrinkles, even with light-colored geomembranes. I don't think it's a good idea to push the wrinkles out in front and then cut out a big wrinkle at the end. That leaves you with a big patch. Especially if it's going to be an extrusion patch, I don't think that's a good idea for the long-term viability of the geomembrane. If you're going to use a thermal patch or a hot air patch that I showed the video of, I think that could be a viable way to do it because the patch is really a good patch. You're actually thermally sealing the patch to the production geomembrane. I showed you a video of it. It looked pretty easy. For those of you that don't know me, this is me in the middle picture right here, actually putting a hot air or thermal patch on a geomembrane. So if I can do it, anybody can do it, all right? And it yields a much better patch, in my opinion, than an extrusion welded patch. Okay, so that's all I've got. Oh, good. We've got about 15 minutes for questions. Let me see. Questions. Okay. First one, I see. Oh, that's great. Somebody got the quiz on slide 37. The answer to the quiz is actually very good. Good job, Nash. The cover soil is being pushed from the top of the slope downwards. Exactly. That's the one thing that was wrong with that photograph. If I go back for everybody, great job picking that up on slide 37 right there. You can see the cover soils being pushed from the top down. That is not a good way to do it. That leads to slope stability problems, tearing of the geomembrane right here. Generally, it's best to push it from the bottom up, as Nash correctly suggested. Okay, let me keep going on the questions. Is there sound? If you have impermeable liners both above and below the GCL, how does the GCL ever get hydrated? Or is it hydrated before the primary geomembrane is installed? Great question. Ideally, that GCL never becomes hydrated. That geomembrane is just sitting there dormant, so to speak, not hydrated. But if a hole or defect ever develops in the primary geomembrane, liquid goes through the defect and it starts hydrating the GCL right at that location. So ideally, we don't want it to hydrate. Now, there is some data that shows when you hydrate a GCL with leachate, the hydraulic conductivity increases versus, say, clean water or deionized water. Yes, that is true. But we really don't want that GCL hydrated for slope stability purposes and bentonite migration purposes. Really just want it to be sitting there just in case a leak develops in the primary. Okay, next one. Question is, are PVC geomembranes less prone to wrinkles compared to HDPE? Yes, the wrinkles are much smaller and not interconnected, and I showed a couple photos of that. Why does the leakage calculator not include reinforced materials? That's a great question. Well, that's a great question. I don't know. I can add reinforced materials to it. And that's very easy because the reinforced materials have very small, very small wrinkles. So that'll be an easy thing to add. So thank you for that suggestion. I'll try to get that done fairly quickly. Here's one. I don't think wrinkle sizes are necessarily controlled by material type. The German and other EU states install HDPEs with wrinkles much smaller and less connected. Absolutely, absolutely. But what is not being said in that question is, let me take Germany, for example. A tent is placed over top of the geomembrane. It's laid flat, and that tent keeps the sun and the thermal exposure off of it so the HDPE doesn't wrinkle. In the United States, I've never seen the tents, and I don't think we have the regulatory push to require us to use what Professor Kerner called as geotents for our geomembrane installations. I don't see that happening in the United States, and that's why the Europeans can do that. And the process, of course, is much slower than our installations. Okay, let me keep going. And if I can't get to everybody's question, there'll be a follow-up podcast next week. And if I don't get to the questions, I will go through the remaining questions in the podcast. Yep, somebody else got soil being pushed down the slope. Good, absolutely. Any comment on how the manufacturing process for HDPE geomembranes impacts wrinkles observed in the field? Flat die versus blown film. Great question. So in general, if it comes out of the blown film, there's actually two sets of wrinkles, and Kerry Rowe's done a lot with that when you open that up, you cut it and open it up, you actually get perpendicular wrinkles. Let me see if I can go back to my Kerry Rowe's slide. Great question on, here. So if you look on this, you see right here, these pretty well-defined lines on the geomembrane. The other wrinkles are pretty random, but so these are manufacturer-induced wrinkles running basically parallel to each other. So if it's just a flat die, so it's a straight sheet out, they don't have those preferred wrinkles. Okay, and again, Professor Rowe's done a lot of work on that. Let's see, what else? Why HDPE, LLDPE are so commonly used if their leakage rate is so much higher compared to PVC geomembrane? Great question. Because after subtitle D, if I go back to the first part of my presentation, HDPE is the only geomembrane specifically listed in subtitle D. It says, the recommended minimum thickness for all geomembranes is 30 mil, with the exception of HDPE, which must be 60 mil. So this kind of gave HDPE a leg into Subtitle D. With some aggressive marketing, HDPE got into municipal solid waste landfills based on its chemical resistance. But any 30 mil geomembrane can be used as long as it's chemically resistant using the 90-90 test. So I surely don't understand why HDPE is used for any non-chemical hazardous facility. For example, potable water. Why would you use it for potable water? Chemical resistance is not an issue there, okay? And as long as your geomembrane passes the 90-90 test, it can be used for waste containment facilities. So why take this extra risk of additional leakage with all the wrinkles? So great question there. Okay, let me keep going. Is dimensional stability an important factor of design? My experience is no one's considering dimensional stability. That's why I put this section of Subtitle D into the presentation that shows in 1988, the US EPA understood dimensional stability. And it says some geomembranes can be manufactured by a calendaring process with fabricated reinforcement called scrim to provide additional tensile strength and dimensional stability. I think it should be included. And now that we can calculate leakage with wrinkles, I think it should be considered. And Professor Rowe's equation for leakage with wrinkles clearly shows a much higher leakage rate. So then we should start talking about dimensional stability to reduce that leakage rate. Another great question. When you recommend wrinkles less than 4 inches, does that mean height or width or both? Another great question. Maybe Ohio EPA could weigh in on that, but I think they are limiting the height to 4 inches, not the width, because generally the width, the wrinkle kind of goes out at the bottom and it can be higher or wider than the height of the wrinkle. But I think Ohio EPA is focusing on the height of the wrinkle. Question is, when regulations to limit wrinkle height, are there any specific ones in effect right now? I think the closest one becoming in effect is the Ohio EPA one. And last I heard it was out for comment, but again, maybe I'll update that for the podcast and figure out if it's been accepted or not. Ohio EPA. Okay. What are the cost benefits between an air patch and a traditional patch? So a thermal or a hot air patch versus an extrusion patch. For me, I think it's a lot easier to put a hot air patch. I mean, I can do it. So that can tell you something right there. Second, I think it's quicker. You don't have to grind the geomembranes. You don't have to extrude the leachate bead on top of it. You put the patch material. Generally, you cut a patch that's like 6 inches in diameter. So if there's a small defect, you've got 3 inches on each side. You thermally hot air it down, and that's it. That's all there is to a thermal patch. So I think it's easier, quicker, and less costly. Okay, let me see what time. I've got a few more minutes. Let me keep going. From a leakage standpoint, does the trade-off to minimizing wrinkles using PVC outweigh liner durability of HDPE? Well, good question. So that gets to the 90-90 testing. Of course, if the geomembrane is not chemically resistant to whatever you're going to contain, that's going to be a durability issue for sure. In terms of other durability issues, HDPE is susceptible to stress cracking around wrinkles, where that won't be the case with a more flexible geomembrane that does not have these large wrinkles. Okay, let me keep going. Why does the leak? Okay, I saw that one. Install, oh, that's the slope stability problem. What liner or geomembrane material would you recommend for ponds exposed to the elements? Oh, great question. So no cover material placed on top of it. There, you clearly need a dimensionally stable geomembrane because it's going to be exposed the entire time. So a reinforced material or some other material that's dimensionally stable. There's an ASTM test method for dimensional stability. It is ASTM D1204. D as in David, 1204. So you can measure the dimensional stability of different types of geomembranes. Pick one that has a low change in volume or a high dimensional stability if it's going to be exposed. And so reinforced materials are a good recommendation there. Okay, let's keep going. Height. Can you provide some geomembrane types with fabric reinforcement? Pretty much every polymer, polypropylene, polyethylene, comes with reinforcement. You can get a reinforced version of the product. For example, reinforced polypropylene, reinforced polyethylene. So there are a lot of flavors of geomembranes with geosynthetic or scrim reinforcement. So just look for a reinforced geomembrane. Let's see. And just before the drainer there, wrinkles lead to loss of contact with underlying materials. How to consider veneer stability for the cover? Oh, great question. I didn't get into stability, believe it or not. But anytime you have a wrinkle, you don't have contact or friction between the geomembrane and whatever's underneath of it. So even though we assume full contact in our slope stability calculations, if we have a lot of non-contact, of course, we're not generating interface strength at those locations. So that's a great question. I've seen slope stability calculations where you reduce the interface strength, and I'm talking about the laboratory interface strength, by a factor. And that factor goes from 5 to 30%, depending on the amount of wrinkles you think will develop in your facility. So if you have an interface friction angle, I'll make up a number, 26 degrees. You would assume 30% of the facility has wrinkles, so you would not have intimate contact over 30%. So you would reduce that friction angle, say by 30%, check your factor of safety. Now that's applying that 30% reduction over the entire length of your two-dimensional failure surface, right? So if you think the wrinkles are predominantly on the floor or predominantly on the side slope, you could isolate that 30% to the side slope or the floor or both, depending on what you think. So that's how people are trying to capture wrinkles in their slope stability calculation by using a factor on the interface strength, because we run the interface strengths in the laboratory without wrinkles. Great question. Jeez. Okay. Oh, that's great. I see Brian Queen weighed in. Ohio EPA, the 4 inches is just the height of the wrinkle, not the width of the wrinkle. Thanks for sending that, Brian. Okay, let me keep going. Is there a study between dimensional stability and leakage rates of various geomembranes? I do not know of one, but that's a great idea of plotting dimensional stability. I could create a very simple graph of that from the leakage calculator by different geomembranes having different dimensional stability and then plotting their leakage on the vertical axis. So I will do that. Good suggestion. Okay, I've got right at 1 o'clock. So let me wrap up, everybody, and let me give my last 3 slides. I will cover the many other questions that were submitted. Thank you so much for all the questions. Let me close so everybody can get back to work. Our next webinar is, here's my contact information if you'd like some additional information, or send me additional questions. I'll record the podcast probably in the next week or two. Our next webinar is U.S. EPA reconsideration of coal combustion residual regulations impacting the geosynthetics industry. This is an update from J.R. Register. He gave a presentation in our Charlotte short course, and Andrew Bittner. So there have been some recent updates or reconsideration of CCR regulations that have an important effect on the geosynthetics industry. That is on October 8th at 11 a.m. Central Time. Finally, visit the FGI website. There's the geomembrane defect calculator. I also have a calculator to compare the cost difference between factory and field fabrication, a pond leakage calculator with a geomembrane, without a geomembrane, and finally, a panel weight calculator so you can figure out what size panels can be shipped under current weight limits on U.S. highways. A lot of other things on the FGI website. I hope you'll stop by there. Thank you so much.